Hello. The topic of today's lab is the RC circuits. And on the board right here, I have a figure that's going to represent what we're going to be working with in lab, or what I'll be working with and you'll be watching. And hopefully you're going to be getting through osmosis, if you want to think about it like that. So this here is the capacitor. I'm going to start off with 100 microfarad as the lab suggests. This is the 100 kilo ohm resistor. And here I have a 10 volt power supply. This here is a switch. So what happens is initially the capacitor is just hooked up to the 10 volt power supply, and then at a certain time it switches over to the resistor. That's what this switch means. So after a certain amount of time, or actually I'll say at time 0, I'm going to do that. Alright, so initially my question to you, if you want to pause the video and think about it, is what is the voltage going to be across this capacitor the moment I move it from here to here? What is the voltage going to be during that initial instant right then? And pause and think about it. The answer is initially it's going to be 10 volts. The initial capacitor voltage is 10 volts. It's got to be, because that's what it was when it was charged up from the battery. It's going to be hooked up to the resistor, and as we talked about in our class lecture, the voltage across the capacitor is then going to leak out, or the charge is going to leak out through the resistor, and the voltage is going to go down. That's what we're going to see. And the way it's going to go down is going to be, hopefully, based upon this equation. It's the same equation you saw in class. This is the voltage across the capacitor as a function of time. This is the initial capacitor voltage, which if the battery voltage is 10 volts, V0 will also be 10 volts. And then this here is time, so it's e to the minus t divided by r times c. So this here is often called a time constant. And it's going to be the most important thing you're going to calculate in today's lab, is the quantity r times c. R times c. And that has very interesting units, as you'll see in some of the other lectures. Actually, his units of seconds. So r times c has units of seconds, which we'll talk about. And it tells you how long it takes for the voltage across the capacitor to go down to, it's about 37% of, I think it's 37.8% of the initial voltage. All right, and so how we're going to measure that is we're going to put basically a voltmeter across the capacitor. So putting a voltmeter across the capacitor will allow us to measure that. Now, rather than using a voltmeter like we've been measuring, in other words, rather than using this, we're going to be using the Logger Pro, which has its own voltmeter that comes with it. It's very simple, but I'm not going to throw this away, but we're not going to use it in today's lecture or in today's lab because it doesn't record it every instant of time. And we want to have a graph. We want the output of today's lab to be a graph that shows how the voltage across the capacitor is varying as a function of time, and the Logger Pro will do that for us. Okay, I'm going to show you the circuit in a moment. Okay, to start off, here's our friend the power supply. Got the plus side and the minus side. That's feeding to our circuit right here. So again, here's the minus, here's the plus, here's the switch. I'm going to bring the camera close so you can really see what's going on. Hope I don't get you dizzy or anything like that. Here's the capacitor. You can see that the negative side is feeding into the lower side of the capacitor, which is also connected to the one side of the resistor. The other side of the capacitor is the white wire, which goes to the center of the switch. So when the switch is like this, it's hooking up the capacitor to the power supply. When the switch is like this, it hooks up the capacitor through to the red wire, which is feeding to the other side of the resistor here. So that once the switch is in that position, you got a circuit going just between the capacitor and the resistor. So my question for you now is, where would I put the meter? Maybe you paused a moment to think about where I'd put the meter, but the meter is this. The meter is this guy, attached to that. So all I have here, it looks like a lot of wires, but all I have is a red wire and a black wire. And if you said I should put them across the capacitor, you're exactly right. That's where I should put them. I should put the red wire here, the black wire there, and now I'm ready to turn on everything and to flip my switch back and forth. So most of the rest of these videos are going to be you watching what happens when I flip the switch back and forth. So you're more interested in the graph at this point than you are in the circuit, because you've already seen the circuit. Alright, so I'll focus more on the application. So I'm actually going to adjust this a little bit. I'll make it so that the minimum is not -10 but 0, and I can make the maximum 10 volts. Whoops. There we go. Alright, because we don't need to see all the negative voltages right now. And I will flip the switch and get the whole thing started. Watch the voltage go up to 10 volts very quickly. There it is, 10 volts. Didn't take long, did it? Now I'm going to press collect, and you're going to see a constant line. Alright, it's starting at 10 volts. I'm going to flip the switch and let's watch it exponentially decay. Here goes. It's going down. We're really interested in the time at which it hits 3.7 volts, for reasons you'll see in just a moment. Great, it crossed it, so I could stop the collection. And I'm going to look at the time it took to get there. Looks like I flipped it off at 7.4 seconds is when it started decaying from 10 volts. And it got to 3.7 volts. So record that time that I just mentioned. 7.4 seconds, that's one of your data points. That's your start time. Your stop time is when it hits 3.7 volts, and that looks like it happened at about 18 seconds. Alright? So the difference between 18 seconds and 7.4 seconds is the time you're interested in. Okay, so in this equation, I'm actually going to write it like this so that you know that the leftmost v is a function of time. This is the initial voltage across the capacitor, which is 10 volts in our case. This is the exponential function that we talked about in the class lecture. And this is time right here. And this is a constant here called r times c. It's the RC time constant. Now what this means here is that this number, r times c, when the time is equal to r times c, remember r times c actually has units of time, seconds, which is interesting. When this seconds equals this seconds, then this term here, this e to the minus t over rc, the term to the right of the v0, if I could select the whole thing, that guy right there, that's going to equal, when t equals rc, I'll write this here, I can say that that term, this term here, I'll copy paste. I can say that this term here is equal to e to the minus 1. I'm going to make that an exponential there, which is equal to e to the minus 1 is equal to 0.368 approximately. Whoops. There. In other words, when the time is equal to the number r times c, the voltage here is going to be equal to about 37% of the initial voltage, or 3.7 volts. That's the significance of the RC time constant.